Hello, we're going to continue our work in probability today, and a reminder we are now on Texan Tests 5. So we're working on Texan Test 5 again, we're on probability 2. So we're on chapter probability 2 in Texan Test 5. And we are looking at tree diagrams as our first topic for today, and we're on page 198 again in Texan Tests 5. So if we have a look at question 3, top of the page, bag A contains 2 blue counters and 3 white counters. Bag B contains 3 blue counters and 4 white counters. A counter is taken at random from each bag. Copy and complete the tree diagram to show all the possible outcomes, work out the probabilities. We'll deal with that in a minute. Now, we have bag A is my first piece of my tree diagram, and then bag B is my second piece of my tree diagram. Now, what should be apparent to us in the question is that these two events are independent of each other. There's no effect. If we get a white counter in bag A, it will not affect how many white counters or blue counters there are in bag B. So these are independent events. That's the first thing we need to figure out, and then looking at our probabilities for getting a white counter in bag A, we have 3 white counters and 2 blue counters, so we have a probability of 3 out of 5 of getting a white counter in our bag A, and then we have probability of 2 blue out of a total of 5 counters in bag A for getting a blue counter. And then for bag B, we have 4 white counters out of a total of 7, and then 3 blue counters out of a total of 7, and these are going to be identical. So all I've done is write out my tree diagram with my bag A and my bag B, and I've written out the probability of each outcome along its branch. So let's have a look at our questions now. Work out the probability that the counters will both be white. So part 1, tell yourself the story. We're going to write this out. So probability, both white. Well, what's that going to mean in terms of outcomes? What outcomes on our tree here meet that criteria? We're looking for the probability of getting a white the first time and a white from bag B as well. So a white from bag A and a white from bag B. That's the only thing that meets that criteria of getting both white counters. So we want to get a white in bag A and a white in bag B. So that's going to be the probability of getting a white in A multiplied by the probability of getting a white in B. And that's what we need to have figured out in our heads for these questions. Now let's sub in, now that we've worked that out. So probability of getting a white in A is 3 out of 5. Probability of getting a white in bag B is 4 out of 7. Just multiply those together and we get 12 out of 35. Part 2. Probability of both blue. What meets that criteria? Well, that would be the probability of getting a blue the first time in bag A and then a blue in bag B as well. So that's going to be probability of getting a blue in bag A is 2 out of 5. Probability of getting a blue in bag B is 3 out of 7. So we get 6 out of 35. Part 3. We want the probability of the same color. Well, let's translate that. What meets that criteria? Well, if we got a white and a white, that's the same color. Or if we got a blue and a blue, that would be getting the same color. So we could get a white and a white, that would meet our criteria. Or we could get a blue and a blue, and that would also be getting the same color. So probability of a white and a white, I know I've already done it here, I'm going to write it out so it's easier for you to see where it's coming from. So probability of getting a white in A by the probability of getting a white in B. Or means add, so plus probability of getting a blue and a blue, 2 out of 5 by 3 out of 7. Out of 7. So we get our 12 out of 35 plus 6 out of 35 is 18 out of 35. And that's our final answer. So again, as we've seen multiple times in probability, our difficulty is not in the maths, this is just multiplying fractions, it's in interpreting the question. So what does it mean to get the same color? It means I could get both white or both blue, and I have to know that those are our two ways of meeting that criteria. Now, if we have a look at the top of the next page, we're looking at question 8, page 199. And we're told a bag contains 3 red cubes and 2 blue cubes. A cube is taken out at random from the bag and not replaced. Then a second cube is taken at random. So I have my situation where I'm taking out my first cube, and then my situation where I'm taking out my second cube. So this is one event after the other. Now, what key phrase do I see in this question that tells me something important? It says not replaced. So and not replaced, we've talked about before, means we are dealing with non-independent events. What happens in this branch will affect what happens here. Why? Because if we get a red cube the first time, there's going to be one less red cube to pick from when we're dealing with our second cube that we're trying to take out of the bag. So let's look at the first selection to begin with. We have 3 red cubes and 2 blue ones, so we have 3 red out of a total of 5 and 2 blue out of a total of 5 the first time. Now what's happened here? We've taken out a red. If we're on this path, we've taken out 1 red. So there's only 2 reds left, but we've also taken out a cube. So there's only 4 cubes left in total. So we have 2 reds left out of a total of 4 cubes left. Now what's happening here with the blue? Well, we had 2 blues to begin with. We didn't take any of them out because we took out a red here. So we have 2 blues left, and we only have 4 cubes left because we took one out when we get to here. So that's our first 2 probabilities up here. Next one, we got a blue this time. So how many reds are left? There are 3 reds left out of a total of 4 cubes left in the bag. And then if we got a blue here and then get a blue again, well, we had 2 blues to start with. We've lost one of them, so we have 1 blue left out of a total of 4 blues. Out of a total of 4 cubes, I should say. So that's my tree diagram done out here, and you can see how this could help you with doing non-independent events and also with independent events, but it can be particularly helpful for visualizing a problem when you're dealing with non-independent events and keeping track of what has affected what. Now, let's have a look at part 2. Part 1 was just drawing that. Find the probability that both cubes taken out are the same color. We come back to the English of a probability question being the main challenge. Same color means we could have gotten a red and a red and then a red, or we could have gotten a blue and a blue. Those are the different ways that we can get the same color, just like we were talking about here. So we would have the probability of getting a red the first time, would be 3 out of 5 by 2 out of 4. Or means plus. Probability of getting a blue the first time is 2 out of 5 multiplied by probability of getting a blue a second time is 1 out of 4. And when we add that up, we get 2/5. And then part 3, probability of getting, find the probability either two cubes are different colors. Well, what are the ways that we could get different colors? Well, we could get a red the first time and a blue the second time, or we could get a probability of getting a blue the first time and a red the second time. So probability of getting a red the first time is 3/5, and then we'd have to get a blue the second time would be 8 2/4. Or means plus. Probability of getting a blue the first time is 2/5. Then getting a red the second time, 3/4. So we get 3/5. Now, hopefully you could see a faster way of doing that, because if we think about it, we either get the same color or we don't. Well, what does it mean if we don't get the same color? It means we got a different color. So these are contradictory to each other. They're opposites of each other. And what do we know about that in probability? Well, the probability of getting a different color must be equal to the total 1 minus the probability of getting the same color. You didn't need to do that in this question. I just want to keep highlighting it over and over again. So, written in more general terms, probability of not A is equal to 1 minus probability of A. And you must have this totally internalized. And we can see that this is true. Probability of different is 3/5 is equal to 1 minus 2/5. And that works out. And that's what we need to be able to do with our tree diagrams.